Hey everyone, Mr. Houck here. In today's video, we're going to be looking at transformations using matrices and area using determinants. Let's go ahead and get started. So first we're going to look at how we can represent vectors and polygons as matrices, and that's going to lead into how we can use these matrices to do some transformations that we've seen in geometry. So in mathematics, matrices are often used to represent vectors. For example, the vector v right here, which is 2i plus 3j minus 5k, can be represented using the 3x1 matrix below, 2, 3, negative 5. Notice that the 2i was represented right here in 2 in the first row, first column. 3j is being represented here in the second row, and minus 5k is being represented as a negative 5 here in the third row. We can also represent polygons using matrices. We can do this by taking all the coordinates of the vertices of the polygon and placing them into the matrix as columns. We would represent an insided polygon using this matrix. So, a polygon with insides, this is how we would represent it. Notice that all the x's are going into the first row and all the y's are going into the second row. So we have x1, y1, this would be one vertex of the polygon, x2, y2, another vertex of the polygon, x3, y3, and so on and so forth to xn, yn, where n represents the number of sides of the polygon. So let's see a few examples here. We want to write each one of these as a matrix. So here we have a square with the following vertices: 1, 1, 1, negative 3, negative 3, negative 3, and negative 3, positive 1. Notice that again, in matrix form, the top row is going to represent the x values, the bottom row is going to represent the y values, and we have to make sure that they're corresponding. So if this, let's take this point for example, 1, 1, if the x value is positive 1, then its corresponding y value would go in the same column. Same thing here, x value of 1, its corresponding y value will go in the same column, negative 3, and so on and so forth. In this next quick example, we have a triangle graphed on the coordinate plane. What I went ahead and did is I looked at the coordinates for each vertex. We have negative 4, 2, negative 3, negative 2, and positive 1, positive 3. Once again, remember that the x coordinates will go in the top row, the y coordinates will go in the bottom row, and they must be corresponding. So negative 4, 2, right here, negative 3, negative 2, right here in the second column, positive 1, positive 3, right here in the third column. And then lastly, let's represent the vector with a horizontal component of 13 and a vertical component of negative 7 as a matrix. Here's our horizontal component x, here's our vertical component y, and we have a 2x1 matrix there. Okay, so let's start talking about transformations, and we're going to start with translations. So recall from geometry that a translation is simply an action that moves a point or figure in the plane without changing its size or shape. When you think translations, you want to think sliding. So in order to translate a figure 4 units left and 2 units up, we would apply the translation rule. xy gets mapped to x minus 4, y plus 2. 4 units left is a horizontal translation, which is why we are subtracting 4 from x representing the horizontal. 2 units up is a vertical translation. That's why we're doing y plus 2 to show that we're taking y, the vertical part, and adding 2 to it. So for matrices, we could represent the translation rule above in the matrix by subtracting 4 from each element in the top row, because remember that the top row are the x's, and adding 2 to each element in the bottom row, because remember that the bottom row is the y's. So that's exactly what we'll do. We would take this square, so this is the square from earlier with these vertices. I went ahead and took the matrix we came up with earlier, and since we want to translate right 2 and down 5, well, I would do x plus 2, because that's right 2, added to all the x values which are in the top row, then y minus 5, so we're going to subtract 5 from all the y values which are in the bottom row, and this is the resulting matrix. If I were to apply all of these points and look at the square, and then if I were to apply all of these points and look at the square, we would see that the original square was moved right 2 and down 5. The next transformation we're going to look at is reflections. So we can use matrix multiplication to perform vector reflections across the x-axis, the y-axis, the line y equals x, which is just a straight line, positive slope of 1, and the line y equals negative x, straight line, positive slope of, slope of negative 1. Now, here's one of the most important parts though. For each of these reflections, we're going to be multiplying the vector on the left side by a special transformation matrix to achieve the desired result. So we're going to be talking about transformation matrices that are going to help us reach desired results. But the important part, the most important part, is that these transformation matrices have to be multiplied on the left side. Okay? Now, here are these special transformation matrices. In order to reflect a figure across the x-axis, we're going to multiply on the left side using this transformation matrix. 1, 0, 0, negative 1. And remember that reflecting across the x-axis, all it's going to do is change the sign of all the y values. Similarly, if I want to reflect across the y-axis, I'm going to multiply on the left by the transformation matrix right here, negative 1, 0, 0, 1. And reflecting across the y-axis, all that's going to do is change the sign of all the x values. And that's what multiplying by this matrix on the left would do. It would change all the x values. If I wanted to reflect across the line y equals x, all I would have to do is multiply on the left side by the transformation matrix right here, 0, 1, 1, 0. And what this would do is it would swap the x and y coordinates with each other. And the next special transformation matrix allows us to reflect a figure about the line y equals negative x. And we would use this transformation matrix right here, again multiplying on the left side, 0, negative 1, negative 1, 0. And what this does is it swaps the y and the x and negative y coordinates. It's essentially going to swap the coordinates and change the signs. Okay, so let's take a look at 2 examples. We want to reflect the vector v, which has a horizontal component negative 2, vertical component 1 across the y-axis. Well, negative 2, 1, if I represent it as a matrix, is this 2 by 1 matrix right here. And we want to reflect across the y-axis, so we need to use this transformation matrix. And remember that we're going to multiply this on the left side. So we're going to take negative 1, 0, 1, negative 1, 0, 0, 1, multiply it on the left side to negative 2, 1 as a matrix. You can see here's the calculation right here. We learned about this in a previous video, and we get the matrix 2, 1. Now notice, again, reflecting something across the y-axis, all it's going to do is change the x-coordinates. Well, the original x-coordinate was a negative 2, the positive 1 for the y-coordinate. Notice that we get, as a result, positive 2, and the y-coordinate remained the same. So it took the negative 2 x-coordinate, changed it to a positive 2, just as expected. In the next example, let's reflect a line segment with these endpoints right here across the line y equals negative x. Well, once again, we have an xy, xy. What I can do is I can turn that into a matrix. So x is on top, 2 and 7. Corresponding y values right below them, 3 and negative 1. And since we want to reflect across the line segment y equals negative x, we need to use this transformation matrix and multiply it on the left side. So 0, negative 1, negative 1, 0. That's right here. Multiply it on the left side by the line segment endpoints put into a matrix. Again, here's all the mathematics behind it, and this is what we end up with as a result. Notice again that what it's going to end up doing is that when you reflect across the line y equals negative x, you end up switching the position of the x and the y coordinates, and you end up changing their signs. So 2 and 3 got swapped with each other. They were both positive, they both changed negative. 7 and negative 1 got switched with each other. The negative 1 changed to a positive 1, the positive 7 changed to a negative 7. So we got the exact desired result that we expected. Okay. Now both of these, if you wanted to, you could also double check with the Desmos matrix calculator. double check this calculation right here. Okay. All right, so the next transformation we want to talk about is rotations. And we are also going to use matrix multiplication to rotate these vectors or figures using another special transformation matrix. Now, just like with reflections, we need to make sure that we multiply this on the left. Okay, very important. I'm going to go ahead and highlight that again. This transformation matrix needs to be multiplied on the left side. But it turns out that if you want to rotate a figure or a line segment, or even just a point, you would need to simply use this transformation matrix, cosine of the angle that you're trying to reflect or rotate with respect to the origin. So cosine, negative sine, sine, cosine. And again, that angle theta is how many degrees counterclockwise you want to rotate around the origin. So here's a quick example. Let's say that we want to take the triangle with these vertices right here and rotate it counterclockwise around the origin by 270 degrees, right? Well, if I want to rotate by 270 degrees, we know that we're going to need the cosine of 270, the sine of 270, and that's been calculated right here. So the cosine of 270 degrees is 0. The sine of 270 degrees is -1. So I went ahead and replaced these values here. So the cosine of 270 is 0. The negative sine of 270 is -1, which is +1. The sine of 270, -1. And the cosine of 270 again is 0. Multiplying it on the left by this triangle written as a matrix. So again, x values on top, corresponding y values on the bottom. If we throw those into the Desmos matrix calculator, this is the result that we get. Now, it might be a little hard to visualize that this triangle has been rotated 270 degrees counterclockwise. So let me show you an image. All right, so here's a Desmos graphing calculator, and let's go ahead and take these points. So here in green, this is the original triangle. And notice that, we'll take one point, for example. Take the point, -2, +1, right here, okay? And if I were to reflect it, or rotate it rather, 270 degrees counterclockwise, well, 270 degrees counterclockwise, we would expect to wind up in quadrant 1. Now, the blue points are the rotated points. And notice, kind of imagine that green triangle, take one of its vertices, rotate it 270 degrees counterclockwise, and you should see the result that is the blue triangle. Okay, so there's a little, hopefully a visual helper as to what just happened. Okay, so we've talked about translations, reflections, and now rotations. Let's now look at dilations and stretches. So, along with reflections and rotations, we're going to use matrix multiplication to dilate figures by given scale factors. To dilate a figure, we simply represent the figure as a matrix and multiply the matrix by the dilating factor as a scalar. And we saw that when multiplying scalars by matrices, when multiplying a matrix by a scalar, we simply take that scalar factor and we can distribute it into the matrix. Now, sometimes we don't want to multiply every single element of the matrix by that scalar factor. Sometimes we just want to stretch a matrix in a specific direction. So these following transformation matrices can actually be used to stretch another figure in a certain direction. Let's say that I want to stretch by a factor of k along the x-axis. Then I can multiply on the left side by this transformation matrix, where k, again, represents how much you want to stretch by, or the factor you want to stretch by. If I want to stretch by a factor of k along the y-axis, I would use this transformation matrix. And let's say I wanted to stretch by a factor of k along both the x and the y-axis. Then I would use this transformation matrix right here. Well, let's see an example. Let's say we want to take the triangle with these 3 vertices, and we want to stretch it along the y-axis by a factor of 3. So along the y-axis, that'll be this transformation matrix, And since we want to stretch it by a factor of 3, we're going to replace the k with a 3. And we're going to multiply it on the left. So we take 1003, because that's where the k would be, multiply it by these vertices, represented as a matrix. So the x values on top, the y values on the bottom. And again, I use the Desmos matrix calculator, multiplied these in the correct order, and this is what I got right here. Now, again, it might be a little hard to tell exactly what happened, but notice that the y values here on the bottom have been multiplied by 3 from the original y values. If you wanted a visual image, again, let's go to our graph. So let me hide these points here. So this, I'm going to go ahead and activate these points. This was our original triangle, these points in red. And after stretching them along the y-axis, notice this is our result, these points in black. So all of these points in red got stretched along the y-axis by a factor of 3. You can see this point here at 0.6 got stretched up to 0.18. This point here at -2.4 got stretched to -2.12. And this point here at 1, -1 got stretched along the y-axis to 1, -3. All right, so that takes care of our transformations. The next thing we want to talk about real briefly is how we can actually use determinants to find areas of parallelograms and triangles. And we're going to start it with a pretty cool little proof. So let's calculate the area of the parallelogram in this picture by finding the area of the overall rectangle, right here, and subtract the areas of all these little figures. It's two triangles and 2 trapezoids. And that's going to give us this chunk in here, which will represent the area of the parallelogram. So we know that, if we look at some of these points here, here's the point 0, 0. We're going to call this point A, comma B. We're going to call this point A plus C, comma B plus D, and this point CD. So notice that this right here and this right here, if I look at this entire length, that's A plus C. So I'm actually going to write that down here. Pick a different color. I'll pick black. So going all the way across, from here to here, that's A. From here to here, that's C. So we can see that the entire length is A plus C. All right. Now going from this point to this point, that's B, and then from this point to this point right here, so from here to here, that's D. So if I look at the sum of this entire side, this is B plus D, okay? So if I wanted to find the area of the overall rectangle, we know the area of a rectangle is length times width. Well, the length here is A plus C. The width here is B plus D. So that's going to give us the area of the entire rectangle. And what we're going to do is we're going to take the area of that entire rectangle and subtract the areas of these little triangles and these little trapezoids, not parallelograms. Okay? So let's look at the area of one of these tiny little triangles first. Well, we know that the area of a triangle is 1/2 the base times the height. Well, the base here, we've already established that the base is C, and the height from here to here is D. So the area of this triangle is 1/2 C times D. Now let's look at the area of this little trapezoid. So the area of a trapezoid is 1/2 the height times the first base added with the second base. Okay? Well, we can see that the height of this trapezoid is B, so we have 1/2 B, and the first base is A plus C, and the second base is just C. So if I took A plus C, that would give me A plus 2C. And notice that this triangle is going to be equivalent to this triangle, this trapezoid is equivalent to this trapezoid, So when I go through and add these together, I'm going to take 2 times 1/2 b a plus 2c. That's coming from this trapezoid. The 1/2 c times d is coming from this triangle. And notice I'm multiplying it times 2 because we have 2 triangles and 2 trapezoids. So using some algebra, a plus c times b plus d, we're using the FOIL method. A times b is ab, a times d, ad, c times b, that's bc, and c times d, that's cd. Then taking this -2 and distributing into the brackets here, -2 times 1/2, well, that's just going to be -1. And then we have the b times a plus 2c. And then -2 times 1/2 is again going to be -1. And then we have the c times d right here. Let's go ahead and take this -b and distribute. So -b times a is -ab. -b times 2c is -2bc. And now let's watch a whole bunch of pieces cancel. This positive ab will cancel with this -ab. This positive cd will cancel with this -cd. And here's what we have remaining. AD, BC, and -2bc. Well, if this is 1bc and this is -2bc, if we combine those together, that's going to be -1bc. And then we had this AD from before. So we get AD minus BC. So the area of this parallelogram is AD minus BC. But remember that the determinant of a matrix, so let's say we had a matrix A, B, C, D. The determinant of that matrix A, B, C, D would be A times D minus B times C. So what it turns out is that the area of this parallelogram right here is equal to the absolute value of the determinant. And the way that the matrix gets set up when you're calculating the determinant is the 2 adjacent sides of the parallelogram. Okay, and what I mean by adjacent sides, the sides that share the common endpoint. So here we have AB, and then here we have CD. Okay, AB and CD right there. Now, notice that if I cut this parallelogram in half, I get 2 triangles. So not only can we calculate the area of a parallelogram using a determinant, we can also calculate the area of a triangle by taking half of that determinant. So that's what these equations right down here represent. The area of the parallelogram, for if we have a parallelogram with 2 adjacent sides, is the determinant AD minus BC, and the area of the triangle is half of that determinant, 1/2 times AD minus BC. So let's give it a try. In this example, we have vector AB is 2, 6, vector AD is 8, 4, and these are both adjacent sides of parallelogram ABCD. We want to find out what is the area of the parallelogram. Well, we have 2, 6 and 8, 4. I'm going to go ahead and turn those into a matrix. And let's take the determinant of this matrix, since the area of the parallelogram is going to be the determinant. So 2 times 4 minus 8 times 6 is going to give us 8 minus 48, which is -40. So that means that the area is 40 square units. Notice that even though the determinant was negative, our area is positive because area cannot be negative. All right, that's going to wrap it up for the notes for today. Again, today's notes were on transformations using matrices and calculating area of a parallelogram and a triangle using determinants.